Hi, my name is Holly Mesrobian, and I'm the Director of Engineering for AWS Lambda. In a little bit, I will be joined by Marc Brooker, who's a Senior Principal Engineer in Serverless. Marc and I work together at Amazon on Lambda. Today, we plan to walk you through some of the key pieces of the Lambda architecture and also some of the innovations that we've been working on. By the end of this talk, you will have a conceptual understanding of the Lambda architecture and understand how your code moves through its systems when you call invoke. First, a little bit about Lambda so you understand the scale of what we're doing. At just 3 years after general availability, AWS Lambda already processes trillions of requests across hundreds of thousands of active customers every month. Lambda is currently available in all 18 AWS regions, and as a foundational service, we launch in every new region that AWS launches. We have a number of customers that are using Lambda to build highly available, scalable, and secure services, including Thomson Reuters, who's processing 4,000 requests per second for its product insights analytics platform. FINRA, who performs 500 billion validations of stock trades daily for fraud and anomaly detection. And Zillow, who uses Lambda and Kinesis to track a subset of mobile metrics in real time. Now, let's turn to why so many customers are adopting Lambda. And it's because running highly available, large-scale systems is a lot of work. First, you need to ensure that your system has load balancing at every layer of your architecture. You do this so you have redundancy in your architecture, but you also so that you can handle more traffic than a single server is able to serve. When you plan to build a new service, you need to plan for and provision for these load balancing layers between primary architectural components. You also need to ensure you have these systems configured with appropriate routing rules such that your load is distributed evenly. Second, on the point of more than a single server can serve, you need to support scaling up so that if you have more traffic than your current service layer can handle, you can continue to serve that traffic. But you also need to be able to scale back down after the traffic peaks so that you're not indefinitely over-provisioned, which of course is wasteful. When you plan to build a new service, you also need to plan for and provision for these auto-scaling layers to sit in front of your fleet, evaluate the capacity of the fleet, and scale up with traffic volume and stress on your server pool, and then back down as peak traffic decreases. Third, continuing on the point of system failure, you need to consider both when a host fails, but what about a complete failure of a data center or availability zone? To this, you need to instrument each of your services with health checks based on key service metrics, and if the service shows as unhealthy, stop routing traffic to that host. Then you need to repeat to ensure you do this for every single system and service component that you build. As a developer, you're now spending a lot of your engineering hours on systems administration. Lambda takes care of all that for you and more, helping developers to focus on business logic and writing code and not administering systems. Today, we will show you how Lambda transparently supports load balancing, auto-scaling, and handling failures, while preserving security isolation and utilization. So let's start off with the Lambda architecture. The Lambda architecture is split into the control plane and the data plane. The control plane is where engineers and developers typically end up interacting with the Lambda service. And on that part of the system, we have a set of developer tools, such as the Lambda console, the CM-CLI, your favorite IDE and tool chains. You're probably familiar with this. And underneath those tools, we have a set of control plane APIs. And these are for configuration and resource management. So when you go and you create a function, upload a function, you end up interoperating with these APIs. And the resource management does the packaging up of your code and ends up putting that up into the Lambda service. And it's at this point where the data plane really picks up. And the data plane picks up, and we're going to first talk about asynchronous invoke and events. And it'll pick up here, And this is where we do both asynchronous invokes, which you're probably familiar with, and also where we interoperate with systems like DynamoDB and Kinesis and SQS. And we have a set of systems here who work together, pollers, state managers, and leasing service. And they work together to process those events. And once those events are kind of processed through that system, they're handed over to the synchronous invoke area of the service. And this is where we're going to spend a lot of our time today. In the synchronous invoke area of the system, we have a front-end invoke, the counting service, the worker manager, the worker, and the placement service. And so let's walk through those system components and talk about what they do. So front-end invoke, it's responsible for orchestrating both synchronous and asynchronous invokes, as we just talked about. And as it's at the very front of the service, the first thing that it needs to do is authenticate callers. So when you call invoke, you want to know that only valid callers are going to make it to your function and call invoke. So the very first thing the service does is it authenticates the callers. And then assuming that that's OK, it will go and load the function metadata. That's things like the environment variables and the limits that you put in when you created the function through the control plane APIs. And then it will go and confirm the concurrency with the counting service. And then what it will do, assuming that we're not exceeding concurrency, then what we'll do is we will go and map that customer function to a worker manager. And we scale up our worker managers based on the current running concurrency. So as your function concurrency scales up, the number of worker managers also scales up along with that, and thereby also your more workers are being scaled up, and this distributes load. So the counting service is responsible for providing a region-wide view of customer concurrency to help enforce those set concurrency limits. And what it does is it's always tracking the current concurrency of your function executing on the service. And if it's below the granted execution, it will automatically be granted execution. And if it hits the concurrency limit, it may or may not be throttled. And the reason I say may or may not is because we want all customers to get their full concurrency. And if we started throttling as soon as you started to get to that limit, then you would really never meet your full concurrency. So we have some intelligence there that helps us make sure that you get the full concurrency. Now this service has to be fast and it has to be resilient. And because of that, it uses a quorum-based protocol, which you'll probably remember from your distributed systems in computer science is a 2/3 agreement type protocol. And as it's accessed on every single call, it can't introduce latency and slow down performance. And so it's designed for high throughput and low latency of less than 1.5 milliseconds. In addition, this is a critical component, and so we make it resilient to failure and make it highly available by distributing it across multiple availability zones. So the worker manager is responsible for tracking container idle and busy state and scheduling incoming invoke requests to the available containers. It handles the workflow steps around function invocation, including environment variable setup and compute metering. It will assume the customer-supplied execution role so that the function code executes with the correct privileges. And when a container is not available, it will handle the scale-up path through the placement service. And it will also spin down sandboxes and workers when they become idle, because we don't want those running indefinitely if they're not being used. And one of the key things that this service component does is it will optimize for running of code on a warm sandbox. And I'm going to explain to you quite a bit through this talk about what a warm sandbox means and what it looks like, so you can stay tuned for that. So the worker is a very important component of the system architecture. It's responsible for provisioning a secure environment for customer code execution. And how it does that, it creates and manages a collection of sandboxes. It sets limits on sandboxes such as the memory and CPU, which is available for function execution. It downloads customer code and mounts it for execution. And it also manages multiple language runtimes. It will execute customer code through initialization and invoke, and it will manage the AWS-owned agents that are required for monitoring operational controls like CloudWatch. It is also responsible for notifying the worker manager when a sandbox invoke completes. And again, this is going to tie back to talking about warm sandboxes. And Marc is going to be talking a lot today about the internals of the worker. So last, the placement service. It's responsible for placing sandboxes on workers to maximize packing density without impacting the customer experience or cold path latency. So really, it's the intelligence to help determine where we want to put a sandbox when we have a function ready for execution. And it monitors worker health and makes the decision as to when to mark a worker as unhealthy. And again, you're going to hear a lot from me about speed. It's designed so that it injects no more than 100 milliseconds into the cold start latency path. Again, our systems need to be fast. And Marc will also be speaking more on this later and how it affects utilization. So now, with a high-level understanding of the primary system components, let's turn back to the load balancing and how Lambda does this behind the scenes. Lambda has several modes based on if a worker is already provisioned, and then if a sandbox is provisioned. And we're going to start off with a scenario where we have an existing worker, but we need a new sandbox. So I'm going to walk you through that call flow. So here we have a customer, and they're calling Invoke, and that hits an application load balancer. And the application load balancer routes that call across a fleet of front-end Invoke hosts. Now, as we talked about earlier, the first thing that front-end Invoke is going to do is it's going to go and authenticate that that's a valid caller. And assuming that it is, and important to note is that we do caching throughout here, of course, for performance reasons. So assuming that it is, it's going to go retrieve the function metadata, and then it will go and check with the counting service the current concurrency and verify that against the concurrency limit. Assuming we can continue on from that point, the front end then goes to the worker manager to reserve a sandbox, and the worker manager says, hey, great, I have a worker, you can put a sandbox on it. And so the worker manager will go and create the sandbox, download the code, initialize the runtime, and call the customer code init, so your init function. And then once that's done, we say that we have a warm sandbox. The sandbox is all ready to go. There's nothing more to do other than to call Invoke. And so the worker lets the worker manager know, and the worker manager lets the front end know, and now the front end can call Invoke. And that causes your code to be run on the sandbox, and at the end of the code execution, metrics are collected up, and then the worker lets the worker manager know that it is idle. And that way the worker manager knows it again has a warm sandbox. So we just left off where we have a warm sandbox. So I want to pick up on that scenario here where we have an existing worker and an existing sandbox. And so we're coming back in with another invoke from the customer. Again, hits the application load balancer, hits the front end. We do authentication. We go and we access the function metadata. And then we go and check the concurrency limits with the counting service. The front end will then proceed forward to reserve a sandbox with the worker manager. And it's this time where the worker manager says, great, I don't only have a worker, I have a warm sandbox there, and it returns that back to the front end. And the front end can then call Invoke, which causes the code, your code, to run, and then again lets the worker manager know when it's done so that it again knows it has a warm sandbox. And so I want to emphasize here, this is where we spend most of our time. This is the call pattern where most of our time is spent on the Lambda service. So load balancing is always necessary, but it really shines when looking at high TPS use cases of consistent traffic that needs high availability and reliability. For instance, web and mobile applications, as is the case for high traffic startups like Bustle and Nextdoor, to enterprises like Capital One and Comcast. And I love this quote from Edmunds around how quickly they were able to build a Lambda-based solution. So in the above example, we covered where we have a worker that's already provisioned, but what happens when we scale up quickly and exceed the capacity of workers, and we need to get a new worker? The overall call pattern is similar to what we have but there are additional systems involved. So let's pick up again. I hope you like my pretty pictures here. So we have the Lambda customer, and there's a new function, or we're scaling up really quickly in this scenario. And we call Invoke, which again hits the application load balancer and goes to the front end. And at this point, you're very familiar with this scenario. You can probably do it in your sleep. We have the front end that authenticates, retrieves function metadata, and then does the concurrency against the counting service, and then proceeds forward to reserve a sandbox with the worker manager. But this time the worker manager says, I don't have a worker and I don't have a sandbox that I can place this function on. And so what it does is it goes to claim a worker from the placement service, and the placement service does its valuation, its intelligence to say, okay, here's a good place for you to provision that sandbox, or provision the sandbox, and so it gives that back to the worker manager, and then we pick up the worker manager is going to go and create the sandbox, download the code, initialize the runtime, and call init on your code. And again, we say here that we have a warm sandbox. And so the worker manager now lets the front end know, and the front end comes in and calls invoke, your code runs, and then it lets the worker manager know again that it's done running, and that way it knows it has a warm sandbox. So a little bit more about the placement service, as it is responsible for ensuring sufficient worker capacity to continue to fulfill worker manager requests for hosts. When the placement service hands out a worker to the worker manager, it provides that worker to the worker manager with a lease of between 6 and 10 hours. The reason for the lease is to enable worker cycling. However, lease duration is also impacted by function duration. You can't have a function that runs longer than your lease. When the worker gets close to its lease expiry, the worker manager must return the worker. And when the placement service receives a worker with an expiring lease, it will re-provision that worker. If the worker manager finds its worker to be close to expiration, it will stop reserving sandboxes on the worker such that all of the sandboxes become idle. And it's at this point that all the sandboxes become idle, that the worker can be returned. So auto-scaling is nearly always necessary. However, when it is heavily used is for workloads where you need to rapidly provision sandboxes for a limited time period and then return them when completed, like with Fannie Mae or Pyron, who scale to between 20 and 50,000 concurrent executions over minutes. Failure is always a possibility, and Lambda is designed to handle cases of failure, whether it be host failure or a complete availability zone failure. Lambda is built across multiple availability zones, and system components are striped across these availability zones with, as we discussed prior, load balancing and redundancy across service layers in the Lambda architecture. In addition, Lambda monitors the health of hosts and removes unhealthy hosts. When a worker becomes unhealthy, the worker manager detects and stops provisioning sandboxes on this worker. And when an entire availability zone fails, the system components continue to execute as shown, although without routing traffic through the failed availability zone. Now, as discussed earlier, Marc will pick up and go into the details on the worker.
Thank you. So it's no secret that, I'll click forward here. There we go. It's no secret that Lambda functions, multiple Lambda functions run on the same hardware and on the same host at the same time. And the reason we do that is, it's just not cost effective for us to buy data center servers with 128 megabytes of RAM. So we run multiple functions on servers at the same time, and this leads to customers. Just one of the most frequent questions we get is, how do we isolate the different functions that are running on a particular worker? And isolation generally means two things to people. One of those things is security, and the other is operational isolation. And by that I mean, how do you ensure that functions run at a consistent performance, or with consistent performance when there are other functions on the same hardware? How do you prevent noisy neighbor impacts, and so on? So to dive into that, I'm going to talk a little bit about the software stack that runs on these workers. So Holly talked about the worker. These are the hosts that run your code. And this is what the stack on a worker looks like. The top of the stack is the most important part, and that is your code. And this is the stuff that comes from your function zip, or it comes from the layers that you heard Werner talk about this morning. The next layer down is the Lambda runtime. So this is the Java or Node.js or Python that comes built into Lambda. And then the sandbox. And the contents of the sandbox is a pretty full-featured copy of Linux. You can go poking around in the sandbox that Lambda functions run in. Look in user bin and user lib. There's quite a lot of stuff there. And that stuff is there because code expects those things to be there. Code that's built on operating systems expects that stuff to be there. The next layer down is the guest OS. And in our case, the guest OS is Amazon Linux. Then we run multiple guest OSs on a box, sometimes many, hundreds or thousands, isolated from each other using virtualization, using a hypervisor. Then there's a host OS, again, Amazon Linux, and this is the thing that hypervisor runs on, and the hardware itself. So this is what it looks like from an isolation perspective. The first three layers, the your code layer, the runtime, and the sandbox, are only ever used by one function. And you will know if you use Lambda that multiple invocations will land in the same sandbox in serial. So if you call the same function once, and then you call it again, and then you call it again, those will all go to the same sandbox in serial. They won't overlap concurrently, and that's where we'll scale up. But we never reuse a sandbox across multiple functions. Then the guest operating systems are shared within an account. So multiple functions within one account will run on the same guest operating system, either at the same time or when we destroy the sandbox for one function and recreate one. So those guest operating systems are shared across functions, but never shared across multiple AWS accounts. And the boundary that we put between accounts is virtualization. And we think this is the minimum security bar for isolation of functions between accounts, and in a lot of ways also the minimum operational bar. So let's step through these layers a little bit and talk about how we achieve operational and security isolation. Underneath the sandbox layer is the same technology that powers containers. And the thing about Linux containers that you'll probably know is Linux containers don't really exist. Instead, containers are a kind of grouping of different functionality that's built into the Linux kernel, a kind of toolbox that you can build sandboxes and containers out of. And we use a number of the tools from this toolbox for our sandbox isolation. The first one of those tools is C groups or control groups. And C groups are a mechanism to say, this process, and obviously anything that it forks or any threads it creates, is only allowed to use a certain amount of CPU, a certain amount of memory, a certain amount of disk throughput, a certain amount of memory throughput. So this is the kind of operational isolation. And this is how, for example, we enforce the maximum function memory footprint using control groups. And C groups are sticky. Actually, all of these mechanisms are sticky. So, you add a process to a C group, and it can't get out of that. It can't take itself out. The next mechanism we use is called namespaces. So there are a whole bunch of resources in the Linux kernel, like process IDs and user IDs and group IDs. And namespaces are just what they say. They're a namespace for those IDs. So if you go digging around inside the Lambda sandbox, you'll see that the process that your Lambda function runs as always runs as process ID PID number 1. And how can you have multiple functions with the same PID number 1? Well, you don't. It's actually just PID number 1 in its process namespace. And it's got a real PID that is not 1. But within the namespace, which is where you are if you're looking at this stuff, you see a namespace set of process IDs. Then there's seccomp, or seccomp BPF. This is a kind of firewall for the kernel. So, the Linux kernel has a whole bunch of syscalls, just exposes stuff the kernel can do, like opening sockets and opening files and so on, or reading and writing from files. And what seccomp lets you do is say, this process can only call these syscalls, or cannot call those syscalls, or can call these syscalls but with only these arguments, or can call those syscalls but not with those arguments. And we use seccomp BPF to cut out bits of the kernel surface area and restrict it to only the functionality that Lambda functions actually need to run. And this is one of the primary security controls. Next, IP tables, EB tables, routing, and various other things provide network isolation, and chroot, bind mounts, and loopback mounts provide the underlying file system. The next layer down in the stack, or in the isolation story, is virtualization and device emulation. And this is using virtualization features built into the hardware, so there's like VTX on Intel, to make the hardware essentially just pretend to be multiple CPUs instead of one. And this is all controlled by the hypervisor and the virtual machine monitor. And I'll get into that a little bit later when I talk about Firecracker. So there are two ways that we build Lambda today. There are two ways that Lambda workers come together. One of those, I have gone way ahead here somehow. Hopefully I can skip back. There we go, a little bit of a spoiler there. One of those is on EC2 instances. So on Monday night, you would have heard Peter DeSantis say, when we started Lambda, we started by building every worker as a separate EC2 instance. And we did it that way for several reasons. One was that's a great security boundary, and the other is that was a fast way to build the system. And we still use this mode today. We run these Lambda workers as normal EC2 instances, exactly the same kinds of EC2 instances you could go off and launch today. And we use the instances on the Nitro platform. The other kind of isolation that we've just started talking about this week is based on our new Firecracker VMM. And on Firecracker, instead of running one instance per account, we run one bare metal EC2 instance, and again, the same kinds of bare metal EC2 instances that you can go off and buy. And we use Firecracker to launch many, many micro VMs, hundreds or thousands of micro VMs on top of that hardware. And this is a more flexible or more agile boundary than instances are for us, and has some really great features. And one of those really great features is simplifying the security model. So instead of having the layer of one function, one account, many accounts, instead we've simplified this down to one function in a micro VM, and then multiple micro VMs across multiple accounts on a piece of hardware. And this is really good for us in a whole lot of ways, which I'll talk about when I get to talking about utilization. But it's also nice for the Lambda programming model because this provides strong isolation even between functions when we're running in this Firecracker mode. So I want to talk a little bit about one of the innovations that we put into Firecracker, which helps raise the security bar. So by way of introduction there, I said we're running hundreds or thousands of Firecrackers on a host. Obviously, these boxes don't have hundreds or thousands of network cards. They don't have thousands of hard drives. But each guest VM, each of those micro VMs, sees a network card and sees a hard drive. And to user space code running in that micro VM, those look like hardware devices. Well, how does this work? This works through the magic of virtualization and a little bit of cooperation between the guest OS kernel and the hypervisor and an implementation of device emulation inside Firecracker. So we use a protocol called virt.io. And this is a way for a driver inside the guest kernel to implement a block device and implement a network card in a way that is very efficient and is very simple and is very secure. So the efficiency, a lot of the efficiency comes from the fact that one of the most important things in virtualization performance is reducing the number of times that the guest OS you have to sort of switch between the guest and the host operating system. And so you can imagine the simplest possible interface is a way for the guest operating system to write a byte or write some words into the host. And it would have to do this multiple times to send a network packet, for example. With Virt.io, instead what it does is builds up some data structures in memory, and then it rings the doorbell on the hypervisor saying, ding dong, there's some work for you to do, there's some packets here for you to send. The device emulation implementation picks that stuff up and sends those to the real hardware. So this is really kind of bread and butter virtualization stuff. The innovation in Firecracker is that this device emulation runs inside a very restricted sandbox. So this kind of a second layer sandbox that just sits around that device emulation code with very few privileges. And what's nice about this is that we get to use all of those controls that I talked about earlier, all of that kind of seccomp, BPF, and so on, to provide an additional layer of security around device emulation. So we built Firecracker in Rust, and we paid a huge amount of attention to the security of that boundary and the quality of that device emulation implementation. But that is also one of the most complex pieces of code. So having the second layer of sandboxing around it provides a second layer of security control, which we think is very important. Next, utilization. And simply, this is about how do we keep those workers busy? How do we keep our servers busy? Well, how do you measure utilization? We think of utilization as the percentage of resources, and their resources mean CPU and memory and so on, doing useful work, rather than being idle or being wasted. And by doing useful work, what that means to me is, ideally, I want every CPU cycle on my worker to be running your code. I want every byte of RAM on my worker to be filled with your data. This is good for us because it's very efficient, and good for you because you get better cache locality and better container reuse, which is good for performance. So the good news for you is that with Lambda, you only pay for useful work. So you don't have to worry about utilization. Utilization is entirely my problem and Holly's problem. This is something we're working on. But there's some interesting topics here, which I wanted to dig into. And one of the things that my team spends a huge amount of work, does a huge amount of work on, is this optimization of utilization. Is the packing onto workers, packing functions onto workers to keep those workers optimally busy. So let's talk about one topic there. Here are 7 sandboxes for a function. Just arbitrarily chose the number 7. And if you saw Holly's diagrams, we've scaled up. There's kind of 7 concurrency going on here. We've scaled up to create 7 sandboxes. The typical kind of distributed systems approach, if you had 7 servers, would be to load balance between them. So you would take some amount of load, and you would try and spread it out across the fleet as kind of evenly as you can. And you do this for a couple of reasons. But the primary reason is that it's really hard to tell how busy computers are. And that's because there's so many bottlenecks. There's the easy stuff like CPU and memory, but there's harder stuff like networks, and even harder stuff like memory buses and caches and so on. So it's very difficult to boil down the busyness of a server to one number or even any reasonable number of dimensions. So what people do in practice is set fairly conservative auto-scaling goals, make their fleet bigger when they hit some kind of CPU utilization and use that as a kind of proxy for the real load, and then load balance across those servers. It's a very time-honored pattern and a pretty great one. We do something quite different in Lambda. We intentionally concentrate the load on the smallest possible number of busy sandboxes. And this is a good thing, and it's a good thing for your code because keeping a small number of sandboxes very busy means that any caches you have or any pre-computed stuff or any connections you have open are kept optimally busy. And that's really great for temporal locality and cache locality. And it's good for us because it gives us a really good ability to auto-scale. So why can we get away with this? Well, we can get away with this because of the semantics of the Lambda API. There is only ever one invoke going on in a sandbox. So a sandbox is kind of busy in a very binary way. It's either got an invoke running on it, or it hasn't got an invoke running on it. So just by counting the number of sandboxes that have an invoke running on them, we can get a very clear picture of the load across the system. And by packing load onto the smallest number of sandboxes, we can simply count the number of idle ones and scale them down. Or we can count the number of busy ones and see that that's approaching the total and start scaling up. So this is all work that placement service does. And it's work that we can do because of the semantics of Lambda. It's another topic in utilization. And this is the really interesting one for me, is how do you pick workloads to run on a worker? So this is a worker, this is a server. Yes, there are servers in serverless. The obvious thing to do here, and the thing that you'd be forced to do if you were kind of building a Lambda for yourself, is run multiple copies of the same workload. So you cut it up into multiple sandboxes, and you run multiple copies of the same workload. It turns out that's a bad thing to do, and that's a bad thing to do because multiple copies of the same workload will have very correlated load. And what that means is when one spikes up on CPU, it's quite likely another one will spike up on CPU at the same time because they're doing the same work. Or on memory usage, or on bus usage, or on network usage, or whatever. So these loads are very correlated. And that really limits how densely you can pack on hardware because your load is going to be very spiky. So what can you do about that? How can you flatten that out? Well, you can take advantage of statistics. And you can take advantage of statistics and simply put as many uncorrelated workloads onto a server as you can. So have a diverse set of workloads instead of multiple copies of the same workload. And this makes the workload way, way better behaved. It really brings down those peaks, brings up the average, and makes it easier to predict scale. So that might sound counterintuitive. So let's see if we can build an intuition for why that's true. When I was in high school, I really enjoyed playing Dungeons and Dragons. And one of the things you do with D&D is throw a 20-sided die. And so here I sat at my desk one day, I threw a 20-sided dice 100,000 times. And I counted each of the 20 values, how often they came up. And you can see that's pretty consistent. I'm obviously quite good at rolling dice. So one night my friends and I wanted to play some D&D, and we left our 20-sided dice at home, but we had some 10-sided dice. So can we just take two 10-sided dice and throw them and add the two numbers up and make that a 20-sided dice? Turns out you can't. So this is what the distribution looks like for the sum of two 10-sided dice. And why is this true? Well, it's true for a very simple reason. There's only one way to make 20. That's a 10 and a 10. But there are a lot of ways to make 12. 10 and 2, 9 and 3, 8 and 4, 7 and 5, and so on. So it just becomes much more likely that you're going to make that 9 and 10 and 11, 12, 13 than you are going to need to make 20. And it turns out the more of these dice you throw, the more of these uncorrelated dice you throw, the better the distribution behaves. And even throwing 10 dice, you can see that I've really pushed down the extremes. It's really unlikely that I'm going to roll 100. It's really unlikely that I'm going to roll 10. So I push down those extremes, and I move the chances of load on my server or some of my dice into a narrow, predictable spike. And the more workloads you put on a box, and the more uncorrelated workloads, and that's very important you put on a box, the better behaved they are in aggregate. So this is something that is very powerful for us at scale. And the fact that AWS runs so many different customer workloads gives us the ability to find uncorrelated ones and put them onto hardware. And this is something that people can't do at lower scale, or doesn't work well at lower scale. And it's fairly unusual in computing to find problems that get easier at scale, so I kind of enjoy this one. It turns out we can actually do better than that, better than just chance, by going and finding workloads that are anti-correlated, ones that spike down on CPU when another one spikes up. And this is something that we've started doing in our placement service, going off and finding workloads that pack together really nicely and make that distribution even tighter than it would be if it was just based on chance. So moving on from this topic, I wanted to talk about another investment that we're making over the course of 2019, enabled by our work on Firecracker. And that's an investment in improving VPC cold start latency. So let's talk about how VPC works in Lambda. What we do in Lambda is when you create a function in your VPC and you invoke it, we go off and we create an EC2 ENI, an elastic network interface, just the kind that you would have in EC2. We attach that ENI to the worker, and attaching an ENI to the worker takes some amount of time, because EC2 has to go back and do a huge amount of rejiggering of the network to get the right packets to go to the right places. And every one of those ENIs consumes an IP address in your subnet. So there's a great model in some ways. One is that it's conceptually simple. Another is that it supports the full VPC feature set. So this is where we started as an implementation. But it does have this huge downside of VPC cold start latency, which we've heard from a lot of customers is something that you care about deeply. So in 2019, we're moving the way this works. We're taking the ENI, and we're moving that off the worker. And instead of doing network address translation between the Lambda function on the worker and the ENI locally, we're moving that into a remote NAT. And we're securely tunneling from the Lambda function to the remote NAT. So what does this mean? Well, in practice, it means that we can use one ENI across many different workers. We can essentially multi-tenant those ENIs. And this lets us use or get away with many, many fewer ENIs. And the fact that we have many fewer ENIs means that a lot of the time we can create them at the time that you create a function rather than at the time the function scales up. And what this means for you is much more predictable VPC latency. So you'll see this coming in over the course of 2019. But also faster scaling, the ability to ramp up faster than you have before without running into limits around ENIs or around IP addresses. But there's another reason this is so important, and that's because it's just way easier to use. One of the edge cases in Lambda VPC is that it's hard to predict how many IP addresses a Lambda function is going to need. So as your Lambda function scales up, every single worker is going to consume an IP address from your subnet. And that makes your network management folks' life fairly complicated. In this new model, things are much, much simpler because for most workloads, we're going to need exactly one IP from each subnet. So that's going to make that management task way simpler than it was in the past. I wanted to get back to Firecracker as we wrap up here a little bit and talk about why we've talked about it so much this week and why you've heard so much about Firecracker. And that's because we're extremely excited about how it enables our innovation. Firecracker gives us much lower startup time than other similar virtualization solutions. It gives us lower memory overhead, very similar performance, but most importantly, it gives us a huge amount of flexibility. And this is giving my team the ability to do all kinds of things like that VPC improvement that you're going to see show up in Lambda over time. So for us, Firecracker unlocks innovation. But for you, Firecracker unlocks higher utilization and higher scale. It unlocks increasing the ability for us to give you ramping up and fast scale ramp up and higher numbers of absolute or higher amounts of absolute scale. So we're very excited about Firecracker, and we're very excited about the stuff it's going to let us do over the next few years. So in conclusion, you heard Holly talk about how Lambda goes together, those front-end components, the invoke service and the counting service and placement. And I talked about the worker and how we think about security isolation and how we think about utilization and how we think about packing. But the great thing about Lambda, the thing I'm excited about in serverless, is that you can leave this room and forget about all of this stuff. It's just been for your entertainment. So I hope you enjoyed hearing about it, and then going off and building things that you don't need to look under the covers, and can just go off and build your business logic and deliver value to your businesses without needing to understand a lot of this deep architecture stuff. Well, thank you very much. Holly's going to join me back on stage for some questions. Just flew through the end of the deck again. Yeah, thank you. Any questions? Yeah. So the question was, does Lambda frontend work with API gateway in the same way? That's probably a great question for Holly.
So, sorry, repeat?
Does the Lambda frontend work with API gateway? Is it integrated with API gateway in the same way?
So the API gateway, actually a very common use case is to call into Lambda functions.
And that invocation works just like you would have seen. API gateway literally calls the Lambda invoke API, just like you can call the Lambda invoke API. And this is one thing that we kind of like architecturally in AWS is using our public APIs because if we need an API or we need a control, chances are you do too. And using our own API gets us a great understanding of what the needs are of customers at scale using that same API.
Yeah, so instead of using virtual PCs or micro VMs, why don't you run it as containers? Lambda functions on top of containers, right, or on top of EKS instead of EC2. Just a hypothetical question.
Sure. Why do we not run Lambda functions as containers? We believe that virtualization is the right security boundary across accounts. I can't go into exactly all of the details why we believe that here, but I'd be happy to talk later. But we think that hardware virtualization should be the minimum bar for code multi-tenancy across multiple accounts.
So with the changes to the ENIs and the concurrency, does that mean we're not going to have to do that crazy concurrency formula any longer in deciding how many IPs we need for a subnet that the Lambdas are attached to?
Yeah, we hope so.
When? When would that, you say in early 2019?
Sorry, over the course of 2019.
Okay.
We'll have more precise dates to share probably in Q1.
Got one over here? Yep. So my question was about the NAT gateway. So it says, it showed up in your diagram that the NAT instance will pop up inside of the VPC. Do we have to pay for the running costs of that NAT gateway? Because they can be quite expensive on a monthly basis? Or?
No, that's something that's built into our architecture. So this is completely under the covers. And other than lower consumption of IP addresses, you're going to see no change in networking capabilities and no change in your bill.
And the last question I had on that was, currently, if you want outbound traffic to go through a static IP address, currently you have to go through a private subnet, routed through a NAT gateway into another public subnet. Is there any way of actually simplifying that so that the Lambda instance can run inside of the public subnet instead, or how will it work?
Yeah, not right now, but that is a great feature request and something that we will take a look at. Thank you.
Thank you.
So I noticed that you had your virtualization directly over hardware. So how do you deal with contention of resources? Is there actually dealing with contention on the network card and on the hard disk? How is that done?
It's a very deep topic and a great question. Probably the best thing I can do is point you at some reInvent talks from last year. There was one that Anthony Ligori did and one that Matt Wilson did. You can find them on YouTube. Or if you find me afterwards, I can find the links for you. That explains in detail how the EC2 Nitro system does that.
Okay, great, thanks.
Hi, I'm over here. I'm very curious about the workers, and I would like to know, how do you keep track of what your workers are doing, where they are at, and where they're done, and what kind of technology and possible languages do you use?
Okay, let's take that one at a time. So how do we keep track of workers? So we have multiple systems that keep track of workers, both in terms of, as you saw, the placement service, as well as the worker manager, and it really depends on the current state and how we're using that worker at that point in time. Can you explain to me a little bit about the languages and where you're going with that? Are you asking about what different language runtimes we support, or?
No, I'm more interested in like the internals, like these workers. You mentioned the state, like where does that state live, and how is it run, like internally?
Inside of the worker. So inside of the worker, we also keep track of all of the sandboxes that we create. So there's data structures inside of our worker that helps to do that. Yeah. Okay.
Sure. It's more of a confirmation here, this side. So I saw you mention, and that was one of the pain area we have with ENI being consuming IP of a subnet. And without understanding the detail about it, what we ended up with, I ended up doing when we created Lambda, which connects to VPC, it goes to direct connect and goes into our data center for transition, during transition phase. I ended up connecting 3 subnets. So from what I understood, it makes sense just to have 2 subnet connected, basically to avoid, because you just need one for failover, let's say.
You're still going to want to have, ideally, one subnet per availability zone that the thing that you're talking to runs in. Yeah. So if your backend runs across 3 availability zones, you're going to want 3 subnets to balance the load and to make that fault tolerance better. If it runs across 4 AZs, you're going to want 4 subnets. And for a couple of reasons. One of them is it gives us more placement flexibility, and then we can make better decisions on your behalf. But it also means that if you don't have a subnet in one of your AZs, we won't be sending load into that AZ, so you'll kind of end up with unbalanced load on your back end. So we think that this new VPC approach is going to make things much easier to balance by reducing the number of IPs that you need. But it's not going to change those best practices about having, essentially 1 subnet per AZ in front of your backends.
I was just thinking, till you guys have that feature available, should I think of reducing 1 subnet just to avoid? But looks like from load balancing point of view, it is better to have 3 subnet connected.
Yeah, from a load balancing and fault tolerance point of view, it's better to have 3 subnets.
Cool. Thanks.
Hi, got 2 questions. First one is about cold start. I've got customers who use an API gateway with Lambda behind them, and they have some very strict SLAs, and they notice that if their cold start happens, they don't meet their SLAs. So they're using these really convoluted frameworks to make sure that they also always have a certain number of Lambdas provisioned. But it's just hard at the moment. Is there anything in the works that allows you just to specify how many warm Lambdas you will want to have provisioned at any given time?
I'll take this one. So we are very aware that for certain use cases, latency can be an issue. And one of the things that we are interested in hearing from customers, and you have just asked about it, which is there a way of guaranteeing that something is warm? And so it's great to hear that that's something that interests you.
Okay, thanks. I forgot my second one. I'll get back to you.
A question regarding more heterogeneous resource allocation potentially, like maybe non-proportional allocation of resources, or perhaps support for elastic GPUs. Is this something that you're thinking of? Do you see any technical implications, or is it more of a business decision?
I would be very interested to hear more about what you would like to see there in terms of controls. So maybe we should chat afterwards. But I think, as a kind of meta point, like one of our goals with serverless is to keep things as simple as possible, and that doesn't mean that we want to compromise on stuff like that, but we want to be very thoughtful about the buttons and knobs and controls we add, because the more buttons and knobs and controls and things we add, the more there is going to be for you and your teams to understand to use Lambda effectively. So we think we can get to most use cases that need additional controls without building additional controls. So that's why I'd like to hear more about your use case and see if it fits into our thinking about how to solve these problems without pushing that complexity onto you.
Well, I guess maybe we can take this offline.
Yep.
Hey, so we have time for just maybe 1 or 2 more questions. I just want to let people know so that if you're coming up to the mic.
Yeah, if that's okay. Is there anything in the roadmap in the future that you're going to decouple the amount of memory and the amount of CPU resources that you assign to Lambda functions? Right now, again, SLA problem, we have to assign well over 1 gigabyte of memory to a Lambda function that only requires 42 megs in order to meet our SLA target, which is just a waste of tremendous amount of memory.
I think the same answer as the previous one. We think that we can get rid of that waste on your behalf without adding the additional controls. So I'd like to, if you have a moment afterwards, or we can get in contact and hear about exactly what you'd like to see there in terms of control. For example, actually, yeah, let's chat afterwards.
Yeah, I'm wondering just what keeps you up at night about this system?
Sorry, I didn't quite catch that.
What keeps you up at night? What are you scared of?
I was talking to Marc backstage before our talk, and I'm actually very excited about where we're at with the serverless technology and where we're going to. And back to the conversation on Firecracker and the innovation that we can drive. I truly believe that this is the future of computing, and so I sleep well at night.
Do you have time for one more? Do you have time for one more, Marc?
Yeah.
Okay.
Hi, thanks. I've done a bit of testing with running many simultaneous invocations of pretty simple functions that do unremarkable things, but I'll see sometimes, well, in the distribution of run times of an instance, I'll see a factor of 5 or 6 easily in the minimum runtime and the maximum runtime. I'd just like to understand what I'm seeing. I'm curious, is that something that you would expect? Is that something like, there's always some number of instances that are unhealthy and that's what it looks like? Just curious if you could comment on that.
We certainly wouldn't expect high variance at steady state. So if you're running a constant load, what we would expect to see is very consistent performance. Obviously, if your code is doing something that takes a consistent amount of time. So if you're seeing something other than that, I'd be interested in getting in touch, and we can dive into that. At not steady state, if you're ramping up or ramping down, you get this auto-scaling behavior that Holly talked about, where we're adding sandboxes or we're removing sandboxes. And for the vast majority of cases where you're seeing inconsistent latency, it's during those scaling times. And that's something that we're working very hard on improving over the next year, starting with the VPC latency, but working on all aspects of that problem.
Well, thank you, everyone. Thank you for coming and watching our talk.